All right, guys, I goofed a little bit with some of our notes. So hopefully we can figure this out. Alrighty, in our table of contents, today we're going to be talking about angle measure and angle addition. So when it comes to figures in geometry, we have our basics, point, line, plane. One level up from that are lines and angles. So we talked about lines. Now we need to talk about angles. We're going to do that on page 8 and 9. So we got page 8 and 9. Now the thing is, in your notes packet that I gave to you, I think I printed the next 2 pages wrong. And I mean, in all honesty, I just tried to record this video and I cut them wrong again. So you're going to see mine a little bit cut already. The next page you probably have is this one here that says angle measure and interior, exterior at the bottom that I accidentally cut crookedly. And then you should have after that names and classification also still together. However, they should have been printed like back to front. So what you should do is actually cut them along each of their lines. Do a better job than I did. Then you're going to take the one that says angle measure, and I'm going to flip it over with angle measure being on the top, but on the back. Okay, so like if I peek right up here, we got angle measure. Then on top of that, I'm going to put the one that says classification, like this. So classification at the bottom. At the top, we have angle measure. And then next, the one that says interior, exterior can go right above that word classification. But I actually need to put the one with names under it. So this is kind of weird. But with the one that says names upside down, I need to slide that under interior and exterior. I'm so sorry, that's so confusing. I meant to have this all perfect for you guys and I goofed it. Once we have that though, hopefully you're able to figure that out. We are just going to flip this over so that then you can see the word names and angle measure. And all of that you're going to actually want to staple together, and now I'm going to pray that my stapler works. Yay. Sorry, that was such a hot mess. So that's going to go on page 8. And then the next one is not the one I need. I think the next one looks actually like this. And I don't want that one. I want the one right after it. See, I was goofing. That says angle addition, angle bisector. That is super easy. You just fold it in half like a book. If you want to be cute, you can cut out the door so that we can open each one on its own. And that's going to go on page 9. Alrighty. So taking a look at angle measure first. Hopefully this stuff seems super easy to you, like the measuring line segments did, maybe before we got to the segment addition postulate. But if I flip this up, what an angle is an object formed by 2 non-collinear rays. And remember, a ray is an endpoint and then an arrow. And they share a common endpoint called a vertex. So we have ray like this. We have a ray like this. Then we get an angle when we take those 2 rays and smash them together so that they share an endpoint and they are not collinear. So kind of if I smash these together right now, they might look collinear, but they shouldn't be if we want an angle. So we have a ray and then a ray, and we get an angle. Is that stuff in between. And then this point right here, we call a vertex. Okay. We also need to talk about how we should name angles so that we can all name them the same way and so that we all understand what we're talking about. I'm going to go from the hardest way to name it to the easiest way to name it. So if we need to be really specific, The best way to name an angle is we put our little angle symbol, and we should walk our way around the angle. So starting at a ray and then going to the vertex and ending at the other ray. So ray, vertex, ray would look like A, B, C. Vertex should always be in the middle. I didn't have to travel that way though. Ray, vertex, ray. I could have gone ray, vertex, ray. So CBA would also be fine. Now, if there's no confusion, because there aren't multiple angles at B, then I could just call it angle B, just by its vertex, because maybe it doesn't have any other angles coming off of that vertex, and so it's simply just angle B. And another way to name it is if we smash a little number in there, then we can call it angle 2. But no matter what, we always have the little angle symbol in front. And no matter what, we have to be talking about the vertex, so B or 2, and then we can put the other points around it if we need to. Okay, flipping that up, we can talk about, my goodness, I kind of cut that off, oopsies, being inside the angle or outside the angle. So I'm going to get a little color here. When we're talking about being inside the angle, then we're talking about the interior of it, and the interior of our angle ABC in this case would be points G and D. E, I don't know, it looks like it's collinear with that one. I shouldn't risk it. So these guys are inside. If we're talking about being outside of the angle, then we're talking about being an exterior point. And that means not like within the vertex space. And so the ones that follow those rules are F and H. Again, it looks like E is on the line to me. So F and H are the ones that we want. Now, when we're talking about different types of angles, this is where I feel like you guys might remember some stuff. So we have different types of angles when we are small, big, or certain measures. So if I am a smaller angle, and when I say smaller, I mean smaller than 90. So if I'm between, not 9. If angle A is between 0 degrees and 90 degrees, then it is acute. And the way that we measure an angle is with this handy little tool called a protractor. Now, I don't know if you'd have a protractor at home, but if you do, it's really fun to measure. You always want to find the center of your protractor and put that on the vertex. And then there's kind of this line along the bottom. You want to line that up with one of your rays, and then you follow that other ray out until it comes to this arced thing around the side here. Now you'll notice it counts 2 ways, 0, 10, 20, 30, 40, 50, or 180, 170. And it doesn't really make sense to count down. And also I'm a small angle, so I should be small numbers. And so you want the inner loop of numbers here. And if I kind of follow that ray out, to me, it looks like it's about 30 degrees. You could always add to the line if you need to be more precise than that, but we're going to just go with 30 degrees. I feel like it looks pretty good. Now, another type of angle that we have, another type of classification of angles are right angles, which are always 90 degrees. And the fun thing here is you can tell everybody else that something is 90 degrees without actually writing down the number 90 by just putting that little square right there, and then you know it's 90. And then you could also be what's called an obtuse angle, and obtuse angles are bigger than 90, but smaller than 180 degrees, because 180 degrees is all the way around. And I feel like now, oh my goodness, I forgot to put another angle on here, and we're gonna have to talk about it. We're gonna have to squeeze it in. It's all good. And so if I wanted to measure this one with my handy protractor, lined up with that right here, this time I'm still counting up 0, 10, 20, but I have to go further around and I get all the way over here. And to me, it looks like this ray is ending between like 130 and 140. And again, if I wanted to be more precise, I might extend this ray out using my straight edge. But I'm just going to go with that's like 135-ish. Now, big old note, I forgot to put one in here. This one needs reworking, this little foldy guy. A straight angle. A straight angle, maybe we call it angle D, would look like this. A, D, B like that. And a straight angle always measures exactly 180 degrees. So that's kind of important to know. Another important thing to know, and we're going to talk about this more on our other foldable as well, is that if I have an angle bisector, specifically a bisector, then it will cut your angle equally in half so that each side is the same. So if DG is an angle bisector of angle CDF, even though it doesn't look like it, it doesn't matter. If they tell you it is so, it is so. Then you can say that each angle on either side is the same because they are congruent halves. So I can say that angle CDG, and again, maybe let me show you with some color. So CDG is this one here. And then GDF is that one there. GDF. If DG is that bisector, then they are congruent to each other. Now, last time when we were talking about segments being congruent, we used little tick marks to show this line is the same as that line. We want to have a similar thing here. And so I don't know if you noticed on some of these angles, I already had these little archy things drawn in. One of my students in the past called it a rainbow, and I haven't been able to use another word since. So to show that these two angles are the same because they are two congruent halves, I can put one rainbow on one and one rainbow on the other. And I tried to do them a little off kilter, so you can see I'm talking about this one and that one. And if they were different than something else, like they're different than this angle here, you could add two rainbows so that you know that this isn't the same as that, they're different than each other. So hopefully that kind of makes sense. And then to make things a little bit trickier, let's jump over. Actually, let's do the angle bisector first. That makes sense because over here we were talking about bisectors, cutting stuff in half. Let's just keep with it. So we open this up and take a look. We have our definition again. So an angle bisector is a ray that divides an angle into two congruent halves or two congruent angles. So we could say that this angle, two rainbows, is the same as that angle, two rainbows. Okay, so if we take a look at example here, we're going to want to mark some things in our picture. So FG is bisecting EFH, which means that this ray is cutting this angle equally in half. So I can say this angle is congruent to that one. If the measure of GFH, oh my word, even I need color, GFH, so I was talking about that angle, is this half parenthesis 10x minus 20. And the measure of EFG, so follow this guy out, EFG, okay, that angle is that 3x plus 25. Find all these other things. So the thing that an angle bisector does for me is since these two halves are equally split, I can set them equal to each other. So I can say that this expression, 3x plus 25, that's talking about this angle here, is the same as this angle right there. So that angle is represented by the expression half, parenthesis 10x minus 20. Okay, so then we got to do a little distributive property here because now I'm just in algebra land. I'm just solving for x. So we're not even in geometry land really anymore. And so if I distribute, I have 5x minus 10, and then we want to get our x's on the same side, so we're going to do the opposite operation. and I'm going to move that smaller one over. And since my x's will be over here, I'm going to also add that 10 over and have 35 equals 2x. Bummer, because now we got to divide by 2. And it doesn't very nicely go into 2, but I'm going to leave it as a fraction, 35 over 2. Then to find all these other measures, I'd have to plug it in. But I don't think I'm going to. It's okay. So let's talk about angle addition postulate. The angle addition postulate is a lot like our segment addition postulate that says if I add up two parts, I get the whole. And the same thing is true if we look at our angle addition postulate. So if K is on the interior of HIJ, then the angle or the measure of angle HIK, so HIK, this angle here, plus the measure of angle KIJ, that angle there. If I add those two parts, then I get the whole measure. So the measure of HIJ, the whole thing. Okay, so hopefully that kind of makes sense. It's kind of like our segment addition, but now it's like in angle form. We add up the two smaller pieces to get the large piece. And so if we try this example here, if the measure of angle AOC, starting right off with a screwy one, AOC is the whole thing. Whole thing is 70 degrees. And then the measure of AOB right here is represented by the little expression half 2x plus 20. And then BOC is x. Okay, we got all three things marked. We're going to add up the two smaller pieces, and that should give me the whole thing. So when I write that out as an equation, like using my angle addition postulate over here, it would be angle AOB, so that first one, AOB, plus the measure of angle BOC equals the whole angle, angle AOC. And then we can just replace each angle with what it measures. So AOB was that half, parenthesis 2x plus 20. BOC was x, and AOC is 70. Now this time, my x's are on the same side, but I still do have to distribute. So we have half of 2, which is 1, half of 20, which is 10, plus x. Then my x's are on the same side, so I'm going to combine like terms. So 2 x's plus 10. Then I'm going to start solving, so I'll subtract that 10. So 2x is 60, and then divide by 2. So x is 30. Okay, so once I know that x is 30, then I can plug it back in to get BOC and AOB. So BOC is actually easy because BOC is just x. So the measure of that angle is 30 degrees. And this is different. This is talking about the value of x. This is talking about the angle measure, so 30 degrees. Then I can kind of find AOB a couple of different ways. I can take the 30 and plug it in there, but I also already know that the whole angle measures 70 degrees. And now I know that part of it is 30. So the other part would have to be 40 because it has to all add up to 70. So I subtract it to find the other two, and hopefully that's not so bad. All right. Let me know if you have questions.